Today our topic is flow of water through soil and effective stresses. Permeability and its concept. The property of a soil which permits the flow of water through it is called permeability. In other words, permeability is the easy with which water flow through the soil. A soil is called pervious when water can flow through it is easily, and is termed as impervious when water cannot flow through it easily. Gravels are high permeable and hence such a clay may be termed as impermeable for all practical purposes. A material is porous only if it contains interstices or voids, but the porous material is permeable if these interstices are interconnected or continuous. Next, importance of permeability. Permeability is a very important engineering property of the soil. The knowledge of permeability is essential for solving different soil engineering problems, a few of which are enlisted below. Number 1, to calculate the rate of settlement of building and other structures. Number 2, to determine yields of belts. Number 3, to analyze seepage through dams and leaves. Number 4, to study losses from irrigation canals, to study losses from irrigation canals. Number 5, to design the filters required to prevent soil piping in hydraulic structures. Number 6, to study stability of the slopes and drainage of the soils. Next is types of flow. The flow of water through the soil may be of two types. Number 1, laminar flow. Number 2, turbulent flow. Number 1, laminar flow. The type of flow in which all the particles of fluid water move in parallel streams or layers without crossing the path of one another is termed as laminar flow. In most of the particle flow problem in soil mechanics, the flow is laminar. Number 2, turbulent flow. The type of flow in which all the particles of water move in zigzag or irregular path crossing and recrossing one another at random is termed as turbulent flow. So, there are two type flow, laminar flow and turbulent flow. The fluid which cannot cross the path one another is laminar flow, and the fluid which cross the path is known as turbulent flow. Next is hydraulic gradient. It is defined as the loss of head per unit length of the flow of water through the soil. It is noted by I. I is equal to H upon L. Head loss shown in figure, the water flow through the soils, sample of the soils whose length is L of the sample. Initially the head is hydraulic head is H1 of the fluid, and finally at the end of the sample the head is H2 from the datum. So, hydraulic gradient, that is equal to loss of head H1 minus H2 divided by L is the length of the soil specimen. So, H1 is the initial head and H2 is the final head. Hydraulic head, the mean head is equal to H1 minus H2 and length divided by length, that is the length of the soil specimen. So, that is clearly shown in figures. So, H1 initial head, H2 final head, the loss of head divided by length of soil sample is known as hydraulic gradient. Darcy law. This law states that for a laminar flow in soils, the velocity of the flow B is directly proportional to its hydraulic gradient I. So, as B is directly proportional to I, or V is equal to K I, where K is a constant known as coefficient of permeability. K is coefficient of permeability. The equation V is equal to K I is known as Darcy's law or Darcy's equation, and is one of the most important law of soil engineering. Further, discharge per unit time, that is equated by Q is equal to V into A. V is the velocity of flow and A is the cross section area. So, Q is equal to K into I into A. It is also known as rate of flow, and area A include the area of the both solids and voids that are present in the soil mass. So, A is the cross sectional area of the sample through which the fluid is flowing. The rate of flow is equal to V into A. So, area A defined as the area of the both solids and voids in the soil mass. Limitation of Darcy's law. Darcy's law is valid only for laminar flow in soils. In fine grained soil such as silt and clay, the dimensions of interstices are very small and flow as laminar. So, Darcy's law is generally applicable only when the flow is laminar. In coarse grained soils, like sand, the flow is also laminar, but for gravels where interstices are very large, flow may be turbulent. It may also be noted that for extremely fine grained particles such as colloids, the interstices are very small and velocity is very low. So, Darcy's law is not applicable. So, this is the limitation of Darcy's law for turbulent flow. Next, coefficient of permeability. From the Darcy's law, V is equal to K into I. So, I is equal to B upon K. If I is equal to 1, then K is equal to B. So, coefficient of permeability K is defined as the average velocity of the flow through the total cross sectional area of the soil under unit hydraulic gradient. So, units of K, the dimensions of K are same as those of the velocity, because I is equal to 1, then velocity is equal to K, then the units of the coefficient of permeability is equal to same as for the units of the velocity. So, it is expressed in mm per second or centimeter per second or meters per day. Next is seepage velocity. We know that velocity is equal to Q divided by area A, B is the velocity of flow, Q is discharge or rate of flow, and A cross sectional area. So, A is cross sectional area is composed of both solids, area of the solids and area of the voids A, B. But actual flow take place only through the voids, not in the solid soils particle. So, through the voids. So, B actual is equal to Q divided by area of the voids A, B, because as AB is less than A, because A is equal to area of solid and area of voids, and AB is only area of the voids, that is less than A. So, when AB is less than A, then V actual velocity ਜਿਹੜੀ that is more than B. So, this actual velocity V actual or true velocity is known as seepage velocity. It is denoted by Bs. So, seepage velocity it is defined as the rate of discharge of percolating water, rate of discharge of percolating water per unit cross sectional area of the voids perpendicular to the direction of flow, perpendicular to the direction of flow. So, therefore, seepage velocity B s is equal to Q upon A V. So, from these equation 1 and 2, B s upon V and is equal to A upon A B. So, B s is equal to V into A divided by A V. So, B s is equal to V and A B divided by A, that is also equal to volume of voids divided by volume B. So, B V upon B. So, that is equal to porosity N. So, A B upon A is equal to N. So, A upon A B is equal to 1 over N. Porosity. So, seepage velocity B s is equal to N is equal to E upon 1 over 1 plus E void ratio. Porosity is equal to N is equal to E over 1 plus E. So, put this value E N porosity at this equation. So, then we have to finalize V s is equal to 1 plus E over E into B, that is the seepage velocity with respect to void ratio. Factors affecting permeability. So, there are various factors that affect the permeability of the soil. So, the following factors which affect the permeability of soils: number 1 void ratio, number 2 particle size, grain size, number 3 structure and stratification of the soil, number 4 shape of particles, number 5 temperature, 6 degree of saturation, 7 water impurities. So, these are the 7 factors which affect the permeability of the soil. Now, further we discuss about these factors one by one. Number 1 void ratio E. So, when greater the void ratio, higher is the value of the coefficient of permeability. Approximately K is equal to A into E square. The plot between E and log K is a straight line. However, it may be noted that the clay which have largest void ratio are almost impervious. So, this is due to fact that the individual void holes in clay are extremely small, through which water cannot pass easily. So, greater the void ratio, higher is the coefficient of permeability. Number 2 particle size. Larger the particle size of soil, higher is the value of the coefficient of permeability. It varies as squares of grain size. The permeability of coarse-grained soil like sand is approximately 1 million times of that of fine grained soil like clay. Number 3, structure and stratification of the soil. For time grained soil, the structural arrangement of soil mass affect the coefficient of permeability. For the same wide ratio, the permeability of the soil is more in case of fluctuated structure as compared to that of dispersed structure. So, number 4, shape of particles. The permeability of a coarse grained soil also depends upon the shape of the particles. It is inversely proportional to the specific surface area, as the angular particles have greater specific surface area as compared with the rounded particles. The angular particles are less permeable than rounded particles for the wide ratio. Number 5, temperature. The permeability of a soil depends upon the temperature of the pore water present in the soils. The coefficient of permeability increases with increase in temperature due to reduction to the viscosity. So, coefficient of permeability increase with increase in temperature due to reduction in the viscosity of the fluid. Number 6, degree of saturation. The coefficient of permeability of a fully saturated soil is always greater than the practically saturated soil. It is because in practically saturated soil entrapped air is present. In practically saturated soil, entrapped air is present, which block the passage of water and reduced permeability. Number 7, water impurities. Presence of any foreign matter in water reduces permeability of soil, as it has a tendency to plug the flow of the water passage. So, permeability of soil is greater with the passage of pure water than with the passage of water containing impurities. So, these are the so many factors which affect the permeability of the soil. Next is measurement of permeability of the soil in the laboratory. The commonly used methods for determining the coefficient of permeability K in the laboratory are: number 1, constant head permeability method; number 2, falling head permeability method. The apparatus used in soil laboratory for determining the coefficient of permeability of soil is termed as permeameter. The apparatus used for constant head permeability test is called as constant head permeameter, and the one used for falling head test is known as falling head permeameter. The constant head permeability test is used for coarse-grained soil like gravel, sand, etc., where sufficient amount of water passing through the soil pores can be collected in given time. So, measurement of permeability of soil in the laboratory. So, constant head permeability test. The apparatus shown in this figure is known as constant head permeameter. Constant head permeameter. So, there are two tanks, one at below the sample and other is above the sample supply tank. So, top tank is known as overflow supply tank. The head is maintained constant and lower tank is a collecting tank. The head is maintained constant at the level H in between the two tanks level of the water. Overflow water that have collected in the measuring cylinder in what time. So, this test is used for determine the coefficient of permeability of coarse grained soils like gravel and sand. The apparatus used for this test is constant head permeameter shown in this front figure. So, the water is flowing supply through the tap at the top of the tank and then this water is flow through the soil samples. The soil samples that is collected in permeameter and below and above both side of the sample provided the porous discs and at the above porous disc then we have covered with the rubber stoppers. So, water is flowing through the top of the tank to the through the soil sample and collected in the lower tank. Level of the water is constant in between both the tanks. So, when water is flowing through this sample and we have to maintain the level by water through the supply tap and when this overflowing water that have collected in the measuring cylinder is shown in figure. So, measurement of permeability of soil in the laboratory procedure by constant head permeability test. Number 1, fill the soil sample inside the permeameter and place the porous disc and rubber stopper in position as shown in figure. So, measure the length and cross sectional area of the soil sample. Number 2, the soil sample inside the permeameter should be fully saturated. Number 3, allow the water to pass through the soil sample under the constant head H. So, this constant head is maintained water level of the supply tank and collecting tank. Number 4, from the collecting tank water overflow in the measuring cylinder and number 5, measure the quantity of the water Q collected in the measuring cylinder in a given time t